it's recording fine. So I'll just ignore it when it's doing that. So we were talking about atomic number, gives us number of protons, which tells us number of electrons. And then we have the number of neutrons. And neutrons don't have an electrical charge, so maybe they seem irrelevant, but they're not. And what they tell us about is something called isotopes. So in a given element, let's say carbon, we're going to talk about carbon first, there can be different isotopes of carbon. And all that means is that there can be different variations of carbon that have a different number of neutrons. In a sample of carbon, you aren't going to be able to tell that one is carbon 12 and one is carbon 13. They all react the same chemically. They all look the same. They all look like carbon. There's a very, very interesting section in the book. Well, okay, interesting to me. I thought it was pretty cool about nuclear bombs, and it has to do with isotopes and how they do actually isolate part of the uranium isotope, I believe it is, and that's how they make the fuel for the bomb. So the actually making of a nuclear bomb, it's not very complicated, but it's making the fuel for it. That was super intriguing to me. I did not know that. I really learned something new. So try to learn like you're not worried about getting a grade. It's so much more fun that way. I know you have to get a grade, and that's part of just being in high school, but learning is so much more interesting when you're just learning it for the sake of learning it. So maybe you could just sort of like pretend like grades don't matter. I know that's like not really true, so it's hard to separate yourself from that. But it's a super interesting section, so enjoy that because it really makes like, what the heck do I care about isotopes? But there's like a real life application of isotopes. So the way you can find out how many neutrons there are, you can't find it out from just looking at the periodic table. You need a little more information. So let me grab my whiteboard so I can write some stuff down here. So they give you the example of first carbon 12. And when we want to distinguish isotopes, this isn't going to write backwards, is it? I hope not. Oh, I don't want a Sharpie. Pen. That's my kids. I always speak in a Russian accent. It's actually my Serbian accent. Okay. So let's see how we can do writing and demonstrating. Okay, so carbon 12. You can write it like this, your abbreviation for carbon is a C, and then you put 12 up there. Or you can write carbon dash 12. A little bit easier this way. I brought a paper towel for erasing, and do you think it's anywhere that I want it? Of course not. Probably sitting on it. Give me one sec, guys. I could pause this, but like in real life, you would just watch me run around looking for something to erase with, right? So, all right, I'm coming back. Don't look. I'm in my pajama pants. Okay, so back we go. Sorry about that little interruption. Easier than just stuff in the video. I will upload this in smaller increments. That will be easier to upload. So we'll talk about this and then probably start another video. Okay, so when I have carbon 12, that tells me, that number right there tells me the number of, make sure I say it right, the number of protons and neutrons. That's what I was going to say. I just want to make sure I say it right. We start talking about all these atomic particles, it's easy to say the wrong thing. So this little, this is not the atomic number. This is the mass number. I think I said that wrong. So mass number doesn't come from the periodic table. So you'd have to be given that you're talking about carbon 12. It's not something that you can access from the periodic table. Atomic number is on the periodic table. So that's that little number associated with the element when you look at it. And then mass number is going to tell me number of protons and neutrons. Okay, so if I know that, and I know the atomic number, I can find everything out. So if I have carbon 12, it's going to tell me that I have, I'm going to just use 12 protons. Oh, sorry, you can't see, can you? Which way do I need to go? 12 protons and 12 neutrons. I also know, from what I just learned from the atomic number, that, no, erase that out of your brain. That's not what that means. It means I have 12 altogether. But, erase that out of your brain. This is what happens when you make videos late at night. You know what you're talking about, but it's not coming out of your mouth very well. We know that the atomic number of carbon is 6, right? So we'll check that I didn't say that wrong to you. Yeah, I know carbon is 6. Okay, so if I know that it's 6, what does that tell me? That there are 6 protons all the time in carbon. Carbon always has 6 protons. That doesn't change. Only neutrons will change. So I have 6 protons. So if I have 6 protons, I have 6 electrons. That's irrelevant to figuring out the number of neutrons, but we can write it down. We know it, just to say we know it. Sorry, left and right is backwards on here. So 6 protons, 6 electrons. And then if I know that there are 12 protons and neutrons all together, if there are 6 protons, then there have to be 6 neutrons, right? Basically, this is saying 12 is the total number of neutrons and protons. Let's just do it that way. So 12 is going to equal 6 protons plus some number of neutrons. So basically then it's 12 minus 6, or 6 plus what gives me 12. Just basic algebra. So 6 neutrons, okay? So now if I have a different isotope of carbon, let's say I have carbon 13. So I'm going to put my little mass number up there. That tells me what? That I have, try to say it out loud. I'm pausing so you can say it out loud so you can see if it matches what I say. That means you have 13 neutrons and protons all together. We know that there are 6 protons, still 6. So I could just say 13 minus those 6 protons gives me 7 neutrons. So carbon 13 is going to have 6 protons plus 7 neutrons to give me that 13 over there. Okay, that's probably a better way to do this. Let me turn my camera a bit so I'm not always, I can cover up the dirty dishes on the table that haven't gotten washed yet. And then, just for reference sake, there are also 6 electrons. So that's just saying the same. It's those neutrons that are changing. Okay, and then one more isotope. The process here is the same. Carbon 14. So when you hear about, what is that? Is it carbon 14 dating? Which one is it? I can't remember which isotope they use for dating things. But it identifies one of the isotopes of carbon. That's what that's talking about when they say that. Okay, so carbon 14 tells me that I have 14 protons and neutrons. And I know that I have 6 protons. So if I minus that 6, that leaves me with 8 neutrons. That's not very big, sorry. So I have 6 protons, just like I always have, plus 8 neutrons and 6 electrons. Same thing. So hopefully this is making sense. Part of it is just clarifying. Oh, dirty dishes, don't look. Part of it is clarifying what are you talking about? Atomic number comes from the periodic table. Tells me how many protons. Mass number tells me how many, because the mass changes a little bit. If there's more neutrons, the mass does change. Electrons don't have any weight, but the neutrons and protons do. So my different isotopes, and we're going to learn more about that later when you can look at a given sample of something, and they'll tell you what percent is each isotope, and we'll do some things with weight and mass, but you don't have to worry about that yet. You just can kind of think ahead that would be something that we work with this, because the weight does change. But again, in a given mass, you can't see any difference. You can't identify carbon 14, carbon 12. Your whole sample is going to have all of those, all the given isotopes of a particular element, but they will all react the same and look the same. Okay. And they also talk about in the book, like, recognizing that it's not like carbon 12 or carbon 12 is not like the normal carbon, and then there's these other kinds of carbons. Like they're all carbon. They give the example that if you had a father and 3 sons, the first son isn't the only son, and the other 2 are just like something else. Like they're all brothers. That's kind of a good analogy, except for brothers are different. I kind of like saying more like triplets. Like, so if I say like, oh, it's a bad habit. I'll try to stop. And now that I've said that, I'll probably say it even more. If you have a set of triplets, they're all triplets. They're all part of that triplet birth. It's not like there was one child and then something else. They're all triplets. They all represent the triplets. They're all equally one of those triplets. I don't know if those analogies help you, but maybe. Okay, what else do we have? Oh yeah, and then that section comes on the nuclear bombs. Super interesting. Make sure you read it. Okay, so we start talking about our first atomic structure. I was trying to scroll, but I'm not on the right screen. First, there was the plum pudding model. It was the idea that there was some kind of a glob. And they're probably, well, I don't think they knew about cells. They wouldn't have known about cells, but it's funny because it sounds like cells, that you've got like sort of this matrix that all the cell organelles or all the atomic organelles sit in, kind of this like pudding model, just that it's like blob of pudding, and you've got some electrons sitting in there, and you've got the center, and they're all just sitting there, essentially, just these electrons kind of just sitting there. But so that was J.J. Thomson. Sounds like a basketball player or something. J.J. Thomson. I don't know why. Sorry, never mind. He developed that plum pudding model, but his student developed the next model. He was shooting some alpha particles through gold foil and catching on the back of a zinc sulfide screen, just what we all spend our spare time doing. No, I think I'd have to go back in the book to look to see how he decided to try that. But that's what he was doing. He was shooting these alpha particles through this real thin layer of zinc or of gold foil. And go and look in the book. I'll try to explain it without I've read it and looked at it. It's always a good test of how well you know something when you try to repeat it. But he thought that he had a theory of what would happen based on the plum pudding model. That if those electrons were just sitting there, and I believe, let me double check, because alpha particles are positively charged. Is that right? Let me make sure I describe this right. There's isotopes. Yeah, yes, alpha particles are positively charged. So his thought was that if all those electrons were just sitting in that plum pudding, then they should deflect as they, or excuse me, no, they would be drawn to that. I feel like I'm explaining this wrong. Let me just look. He reasoned that if the plum pudding model was correct, the alpha particles would pass through the foil without changing their direction much, because the positive alpha particles would be attracted by the negative plums, the electrons, but repelled by the positive pudding around it. Sounds really funny explaining it this way. And since the plums were randomly distributed, in theory, around the middle there, that the alpha particles would be attracted and repelled in many different directions, and then essentially they would just go straight through. But they didn't do that. They did something different than what he expected. He found that some went through and were being deflected over to the side, and then some were concentrated right in front. So read through that. I'm not doing the best job of explaining it, so I apologize. But I think if you read through it, it will make sense, because the author of this book is really good. I really do like how, I think it's a she. Is this a she? I don't know. Or the last name is on there. I want to give credit where credit is due. This author really does do a nice job of taking something super complicated and putting some nice lay terms to it to make it make more sense, and then giving the more scientific terms. But what you'll see is a nice diagram on page 97 that helps you to see what he saw in that experiment, because what he basically came away from is that the electrons aren't just sitting there like blobs, but that they're moving. And so, let's see. So he developed his model of the atom, which theorized that the protons were clustered at the center and the electrons were circling around the outside, rather than just sitting still in the plum. So we have the plum pudding model, which kind of looks like these electron blobs are just kind of sitting around the nucleus. And then we had his student Rutherford, who realized, no, these electrons must be moving. And so his experimentation helped us to develop that model further. And he didn't know about neurons yet. That was not discovered yet. Okay, so they stop after we talk about Rutherford, and we have a whole section on light. And you might go, what in the world? Why did we start talking about light? And I feel like I'm doing physics now, not chemistry. I kind of felt that way. But it's a beautiful segue, a long one, to understanding the next atomic model. So it's actually pretty interesting. It's like all this stuff does come together with having an actual point. So hang in there. So we're going to talk about the nature of light, first of all. Light, as we learned before, doesn't have any mass, and it doesn't take up any space. But strangely enough, even to scientists, it can behave like a wave, and it can behave like a particle. So a wave is something that moves like a wave, like waves on the ocean. Just nothing complicated. But it can behave like a particle too. And so we're not going to talk fully, we're going to talk more about its properties as a wave, but it's called the particle-wave duality theory. And this does confound scientists too. So if it's kind of like the Trinity. It's kind of confounding. We don't fully understand it, but we accept it. And when we see Jesus, we will understand it fully. But like our brains cannot fully grasp it. And that's kind of how it is with light. But we can study it and we can learn about it. Sorry, I hear one of my kids coughing. Sometimes when they cough a lot, that turns into throwing up. And I'm really hoping that's not what's happening here. I think everyone's okay. Okay. So if we are studying light as a wave, there's some things we can describe about it. We can describe the wavelength. So if we look at You know what? I'm going to pause this and I'm going to start another video so that they're easier to upload.